Welcome to the first video in the series about our new unit, Dynamic Equilibrium. In this video, we're going to explain what chemical equilibrium is and identify the requirements that are necessary for it to take place. In order to explain what dynamic equilibrium is, we can start with a fairly simple reaction, the ionization of ammonia, NH3, to form ammonium, NH4. We know that this reaction occurs because when bases such as ammonia are put into water, the nitrogen can use its lone pair to pull the hydrogen off of water, break this bond, and turn its bond into a lone pair on oxygen, therefore forming ammonium, NH4, and hydroxide, OH-. Now, one of the interesting components of watching nitrogen-based bases work is that the reaction is actually completely reversible. So we know that all negative charge will naturally attract to positive charge, and we know that electrons are constantly repelling from each other, which means that the three lone pairs on oxygen in hydroxide are going to repel each other, and it is possible that one of the lone pairs can attract to one of the hydrogens on ammonium, NH4, pull it off, break the bond, and give nitrogen back its lone pair that it started with here. Now, as stated before, this is exactly the reverse reaction of what we saw before, because the lone pair is used to take a hydrogen off of ammonium in order to give us back water, and when the ammonium loses one of its hydrogens and the nitrogen gains its lone pair back, we end up with ammonia once again. So we see again that this is literally the reverse of the reaction that we saw before. Now, the even stranger part is that if we ask which of these two reactions it's happening at a given time, the answer to that is actually both. What that means is that a certain amount of NH3 is undergoing the base ionization where we produce OH-, and a certain percentage of that OH- is going to take the hydrogen back from NH4+ and give us water again, such that both reactions are happening simultaneously. That means that we can rewrite this equation like this, with a unique bidirectional set of arrows like this to show us that NH3 and water are undergoing an ionization to make NH4+ and OH-, but simultaneously the reverse reaction is also happening. This is what we call dynamic equilibrium because both reactions are simultaneously happening at the same time, and eventually what is going to happen is that the rate of the forward reaction, which we write as rate subscript F, is going to become equal to the rate of the reverse reaction, rate subscript R. And that's why these arrows are written like this, where the forward arrow and the reverse arrow are written of exactly the same length to show that the forward direction and the reverse direction are happening at the same rate. Another way of describing this situation is that the rate at which the products are formed, in this case ammonium and hydroxide, is exactly the same as the rate of the products reacting in order to give us the reactants once again. This means that both the reverse reaction and the forward reaction are happening not only simultaneously, but happening at the same rate. And when we have achieved this situation, we have achieved what we call dynamic equilibrium. And the next video will go over in a little bit more detail what exactly this means. So what conditions are necessary in order for dynamic equilibrium to occur? The first of which is what we call a closed system in which no matter can escape from the chemical reaction. So what a closed system means is that all of the reactants and all of the products can stay within the chemical reaction and cannot escape, which means that the mass of the given reaction is a constant because no matter can get in or out of this reaction. And there's a very good reason why this is a requirement. If we consider this double displacement reaction here, the reaction of acetic acid and sodium hydrogen carbonate, if this were to take place in an open system, the mass of this system we would expect to decrease, and that's all because of carbon dioxide gas. Because a gas is produced by this reaction, if we did not keep this reaction in a closed system, if it existed in an open system, the carbon dioxide can simply escape from this beaker where it's taking place, which means that the mass would decrease. Now, if we get rid of carbon dioxide, if all of the carbon dioxide produced escaped from this system, is the reverse reaction possible anymore? Well, the obvious answer is no. We wouldn't be able to make carbonic acid anymore because there is no carbon dioxide to synthesize with water in order to make carbonic acid, so the reverse reaction isn't possible, and therefore dynamic equilibrium, where the forward and reverse reactions become equal, is no longer possible. Now, a second requirement is not really a requirement, but more an observation that occurs. If we go back to the acid and base ionization that we see here, if the reaction is at equilibrium, that means that the forward and reverse reactions, by definition, are occurring equally. Now, if the rate of formation of products and the rate of formation of reactants is identical, that means that none of the concentrations are going to change, and therefore all of the concentrations of all of the reactants and products will remain constant. Now, if that means that OH minus is constant as well, would we see the pH changing at this point? Well, again, that answer would be no, because this amount of OH minus, no matter how much of it is produced, a certain amount of that is going to be consumed to do the reverse reaction at the same time. Now, even if we don't know where delta H is, we don't know if this is an exothermic or endothermic reaction, but if both directions are occurring at the same rate, presumably that delta H is not going to change as well, meaning the temperature of this reaction is going to stay constant as well. Effectively, what we're saying here is that if you were to look at the conditions of this reaction, even if the forward and reverse reactions are happening, we would not see any observable change as long as the reaction occurs at equilibrium. So would we see, perhaps a better word for see is, would we observe any changes occurring? Well, again, that answer is no. We wouldn't see a temperature change, and we wouldn't see any measurable pH change, but that doesn't necessarily mean that no reaction is happening. This condition is what we call a lack of what we call macroscopic changes. Another word that we can use instead of macroscopic is that we would not be able to observe any changes that are occurring in this reaction. Now, from this, we can come up with a slight quantification, which we're going to expand on in the next video. As we've already established, the concentration of our primary reactants and products, NH3 and NH4+, do not change, meaning that they're both constant. Now, if these don't change at all, then the other reactants and products are going to remain constant either. And from this, we can codify a specific relationship between the concentration of all products within the reaction and the concentration of all reactants in order to define a standard measurement that we can use in order to actually do calculations, which we will look at in subsequent videos. So in systems in which a dynamic equilibrium is possible, if we take the concentration of all products that exist within the equilibrium system and divide them by the concentration of all reactants within the equilibrium system, we can define this as a constant for the reaction, which we will simply call KEQ. K, again, referencing the reaction constant based on temperature that we saw with rate law, and EQ signifying that we are at equilibrium. So not surprisingly, KEQ is what we term the dynamic equilibrium constant, which will become important for calculations that we will do in subsequent videos. In the next video, we're going to explore this notion of constant concentrations that occur when the rates become constant, and look at a way that we have to more easily visualize the process of a dynamic equilibrium system forming.